In nature, we come across many elements. Some of them have nuclei which are highly stable, while others are relatively less stable. For example, the nucleus of iron is very stable, while the nucleus of uranium is considered to be unstable. To understand this aspect of nuclear stability, we should first study about Einstein's mass-energy equivalence relation. According to Einstein's mass-energy equivalence relation, energy and mass are equivalent to each other, and one can be converted into the other. When a certain mass m is destroyed completely, the amount of the energy released is given by Einstein's mass-energy equivalence relation as E is equal to mc square, where c is the velocity of light, which is equal to 3 × 10⁸ meter per second. Here, E is referred to as the energy equivalent of the mass. According to Einstein, mass is a form of energy and it can be converted into other forms of energy, say kinetic energy, and vice versa. Let us now look at how much energy is released when one atomic mass unit of mass is completely destroyed. We know that the energy E released during this process is given by E is equal to mc square. Substituting mass m as 1 amu, which is equal to 1.66 × 10⁻27 kilogram, speed of light c equal to 3 × 10⁸ meter per second, and simplifying, we get E is equal to 1.4924 × 10⁻10 joule, which can also be expressed as 931.5 million electron volt. Let this be equation 1. For a mass of 1 amu, the energy equivalent is 931.5 million electron volt. For any mass m equal to delta m, the energy equivalent is given by E equal to delta m into 931.5 MeV. Therefore, we can say that 1 amu mass is equal to 931.5 MeV by c square. This is an enormous amount of energy release. Let us now study the concept of nuclear binding energy in light of Einstein's mass-energy equivalence equation, considering a sample nucleus, say an oxygen nucleus. An oxygen nucleus is made up of 8 neutrons and 8 protons, and hence its atomic number Z equals to 8 and mass number A is equal to 16. The mass of each proton is Mp is equal to 1.00727 amu. The mass of each neutron is Mn equal to 1.00866 amu. And that of an electron is Me equal to 0.00055 amu. The total mass of the constituents of the oxygen nucleus is the sum of the masses of 8 protons and 8 neutrons put together, and this is equal to 16.12744 amu. Theoretically, this is the expected mass of the oxygen nucleus. But the actual mass of the oxygen atom M, determined experimentally using the mass spectroscopy principles, is 15.99493 amu. When the mass of the 8 electrons is deducted from this, we get the mass of the oxygen nucleus as 15.99053 AMU. Hence, we observe that there is a difference between the theoretically expected mass of the nucleus and the actual mass of the nucleus, which was determined experimentally, and this difference is observed to be 0.13691 AMU. This difference between the theoretically expected mass of the nucleus and the actual mass of the nucleus is called the mass defect, denoted by delta M. Mass defect delta M for a nucleus can be determined by equation 2 as shown, where Z is the atomic number of the element, A is the mass number, A minus Z denotes the number of the neutrons in the nucleus, Mn is the mass of each neutron, Mp is the mass of each proton, and M dash denotes the actual mass of the nucleus. Equation 2 can also be written as MTH minus M dash, where MTH is the theoretical mass of nucleus, which is equal to Z into MP plus A minus Z into Mn. Since the mass of the nucleus is less than the sum of the masses of its constituents, there exists a mass defect. Hence, the equivalent energy of the nucleus is less than that of the sum of the equivalent energies of its constituents. If an oxygen nucleus has to be broken up into its constituent protons and neutrons, energy equivalent to the mass defect needs to be supplied. The energy equivalent to the mass defect is obtained by the Einstein's mass-energy relation. This energy is called the binding energy and is denoted by EB is equal to delta M into C square, if delta M is taken in kilogram. If delta M is taken in million electron volt, then EB is equal to delta M into 931.5 as discussed earlier. Energy equal to binding energy is released when the constituents of a nucleus are brought together. This same energy is required to break a nucleus into its constituent nucleons. For the oxygen nucleus, substituting the values of mass defect delta M equal to 0.13691 AMU and simplifying, we get EB is equal to 127.5 MeV. The value of EB can be obtained in joule if we take delta M in kilogram. The ratio of the binding energy to the mass number A of the nucleus is called as the binding energy per nucleon or average binding energy and is denoted by EBN. EBN is equal to EB by A. Average binding energy is the energy required to remove a nucleon from the nucleus. For the oxygen nucleus, the average binding energy is equal to 7.96875 MeV per nucleon. Average binding energy of various nuclei indicates the relative stability of the nuclei. High average binding energy values indicate highly stable nuclei, while low average binding energy values indicate low stability for the nucleus. We can understand the relative stability of the various nuclei of the elements by plotting a graph between the average binding energy values on the y-axis and the corresponding mass number values on the x-axis. From the graph, we see that for nuclei with mass numbers less than 30, the average binding energy values are relatively less, indicating relatively low stability for those nuclei. The average binding energy is almost independent of the mass number A of nuclei in the range of mass numbers between 30 and 170 and is nearer to the maximum value of the average binding energy. This indicates high stability for the corresponding nuclei. The average binding energy is maximum for a nucleus of iron of mass number A equal to 56 and is equal to 8.75 MeV. We also see that the average binding energy has a value of 7.6 MeV for A is equal to 238. It is observed that the binding energy per nucleon is lower for both light and heavy nuclei. That is, for nuclei with mass number A less than 30 and greater than 170. From the observations of the graph, a few conclusions can be drawn regarding the type of forces that exist between the nucleons in the nucleus. To produce a binding energy of a few MeV per nucleon, the force between the nucleons should be attractive and sufficiently strong. The constancy of the binding energy in the range where mass number A varies from 30 to 170 shows that the nuclear forces are short-ranged. A nucleon will be under the influence of some of its neighbors, which come within the range of the nuclear force. If any other nucleon is at a distance more than the range of the nuclear force from the particular nucleon, then it will have no influence on the binding energy of the nucleon under consideration. If a nucleon can have P neighbor within the range of the nuclear force, then its average binding energy will be proportionally to P and hence can be written as pK, where K is a constant having the dimensions of energy. If nucleons are added to the nucleus to increase its mass number A, there would be very little change in the average binding energy of each nucleon, as most of the nucleons inside a large nucleus reside well inside the nucleus and not on the surface. Hence, the average binding energy remains constant and is approximately equal to pK. The property that a given nucleon is influenced only by nucleons close to it is referred to as the saturation property of the nuclear force. This is observed in large or medium-sized nuclei. A very heavy nucleus, say A is equal to 240, has lower binding energy per nucleon compared to that of a nucleus with A is equal to 120. Thus, if a nucleus A is equal to 240 breaks into two A is equal to 120 nuclei in a process called the nuclear fission, the nuclei get more tightly bound and hence become more stable in the process. This shows that a large amount of energy would be released in this process. This is the reason for the high energy release in nuclear fission. Similar is the situation when two very light nuclei with A around 10 join to form a heavier nucleus by a process called the nuclear fusion. The binding energy per nucleon of the fused heavier nucleus is more than the binding energy per nucleon of the lighter nuclei. This means that the final system is more tightly bound than the initial system. Again, energy would be released in such a fusion process. Thus, we observe that for most of the nuclei, the binding energy per nucleon is very large compared to the binding energy of atoms in a molecule. Thus, there should be a strong attractive force among the nucleons in the nucleus, which can bind the nucleons together in the tiny nuclear volume in spite of the Coulomb repulsive forces that exist between the positively charged protons. This force is called the nuclear force. From our analysis of the nuclei, we come to know some features of nuclear force. Nuclear force has to overcome the Coulomb force between protons and keep them together. So, nuclear force must be stronger than Coulomb force. As gravitational force is weaker than Coulomb force, we can conclude that nuclear force is stronger than both Coulomb and gravitational force. Therefore, nuclear forces are the strongest forces in nature. This can be observed from a graph of nuclear force versus distance between nucleons. Here is the graph showing a plot of potential energy between a pair of nucleons against their separation. It is observed that potential energy is the least for a distance r0 of about 0.8 Fermi. From the graph, we see that the potential energy is very high for r values less than 0.8 Fermi, which implies that the nuclear forces are very strong in that range. This force falls rapidly to zero as r value crosses 0.8 Fermi. Nuclear forces bind the nucleons together. That is, they exist between two protons, two neutrons, and also a proton and a neutron. Therefore, nuclear forces are independent of the charge and the nuclear force acting between two neutrons, or between two protons, or between a neutron and proton, is approximately equal in magnitude. We have simple mathematical equations representing the Coulomb force and the gravitational force, but we do not have any such mathematical expression for the nuclear force.